Hi everyone, we have pursued the speed in a SerDes for a long time to maximize the bandwidth throughput, minimize the pin counts, increase the energy or power efficiency, maximize the maximum available area or density, etc. So we are very excited to achieve 224 gigabit per second per lane SerDes now. Before moving too far, we need to pause a bit and do you think if moving to a line rate beyond 224 gigabit per second is necessary? Could you tell me why I should not have a higher speed SerDes anymore? Here shows lots of the published 224 gigabit per second PAM4 SerDes, but we haven't seen any higher speed than 224 gigabit per second yet. The first one is the design challenge. We may face from the limited device performance. If the 3 nanometer or 2 nanometer cannot have an intrinsic cut-off frequency FT higher enough for the analog device to operate at a higher data rate, those I/O cannot go faster. Therefore, we might hit the speed barrier from the existing device, and we must stop a higher speed in a SerDes. In addition to the performance limitation, what else could be the limitation? Correct, power. For example, we know the digital power should scale with the speed from the CVF power if both capacitance and supply voltage are the same. Unfortunately, that's not exactly true from the real power consumption. Instead, the power versus speed could be a nonlinear transfer curve shown here. Could you please tell me why is that? Think about the fan out of the digital gates for 5 seconds. Yes, from the digital circuit images, you might keep the fan out of 4 as your own rule of thumb to provide the best driving capability and lowest power from Professor Rabe. Unfortunately, if the device ID set was not high enough to drive a big load over the capacitance fast enough, then the fan out of 4 would end up with a slow rise 4 times during the logic transition, such that the speed isn't high enough. Therefore, doubling the speed may not doubling the power with the same energy efficiency. Instead, it could quadruple the power with doubling energy efficiency due to a small digital fan-out is needed, along with a longer buffer chain. If that's the case, the higher speed may degrade the power efficiency, and we should think about the option of reducing the line rate. From a simple digital gate, we know the power limitation in speed. What else do you remember? Perfect. Let's recall the analog block quickly. First, the TX design should starting from the TX driver, then scaling back at the multiplexer or serialization. As you can see, the size and power of the TX driver should stay similar to the 2 speeds, but the fan-out of the cascaded multiplexer can be close to 4 if the speed is half. Therefore, the TX power will be reduced a lot. In addition, the TX PL's power could be smaller to get a similar jitter performance at a lower speed. Back to the TX clock distribution. No matter CML or CMOS buffers, loss power can be reduced a lot at half rate to get a similar driving strength and thermal noise at the full rate. How about the RX? Great. You know, the RX must take whatever signals at the front end and recover to the right digital level in bits, such that the bit array could be as little as possible, or zero ideally. Therefore, the half rate may lead to a half channel loss if the channel length and material are the same. Therefore, the RX can be simplified with a simple CTOE only. In addition, the CTOE's required bandwidth will be roughly half, and the power can be half at the front end. Since the signal loss is half, we don't need to have a very high gain to boost the swing for the sampler. Therefore, all the CTOE stage, including the VGA to the summing amplifier and sampler, should have a half power. More re-architected circuit images like the full-rate CDR could be invented to achieve a very low latency to improve the JTAL. Even though a DFE is needed, the low data rate will even get rid of the loop-on-loop topology, such that the direct feedback topology will reduce the power a lot, owing to its simplicity. Okay, during those circuit images in the performance and power, what's the area benefit? Yes, the area must be small at the low data rate. It's very obvious that the circuit block has been simplified a lot, owing to the low loss, non-oversized digital gates, and relaxed analog performance. Therefore, having less required functionality and few gates, device, passive elements, RLC, etc., we can reduce the area a lot. Does that help reduce the total chip area? Yes or no? Traditionally, the bump pitch of the featured package is on the order of 150 micrometer to 200 micrometer. Therefore, the chip area is the bump limit, not the circuit block in the design. Most people notice that and keep shrinking the bump pitch. For example, TSMC can shrink the C4 bump from 130 micrometer to 90 micrometer. Furthermore, TSMC even applied 2.5D technology to shrink the micro bump to even less than 40 micro pitch. So again, with the latest technology, we are not bumping limited area anymore and should stop pushing the data rate high with a complicated circuit block filled under the bump in the old way. Okay, we are summarize the low speed benefit of the PPA matrix in a SerDes. What's the other critical matrix in the PPA? Think about the temperature images for 5 seconds. Bingo! Thermal runaway could be a concern, especially the increased temperature impact on the most advanced 16 nanometer to 3 nanometer FinFET device self-heating and aging. So, how do we mitigate the FinFET heating and aging issue? Okay, where is the thermal issue coming from? Yes, the current over power consumption in CVF. So, reducing the speed can reduce the current density in the unit device of the FinFET. So, the implication of reducing power from the low speed operation will also help stabilize the thermal and reliability. Then, how's the power looks like if we reduce the power from 32 gigabit per second to 16 gigabit per second NRZ SerDes? We've explained why the low channel loss benefit the better energy efficiency. Also, the insertion loss versus the data rate shows ballpark of 36 dB loss at the 16 GHz for the 32 gigabit per second operation, but only 18 dB loss at 8 GHz for the 16 gigabit per second operation. Therefore, it's doable with the CTOE only and TX-FFE to get 3 picojoule per bit efficiency at 16 gigabit per second, while we must need at least 7 picojoule per bit at 32 gigabit per second. To get the transmission bandwidth throughput, 2 lanes 16 gigabit per second compared to 1 lane 32 gigabit per second still can provide 32 gigabit per second bandwidth per lane with only 6 picojoule per bit, which saves 32 milliwatt per lane. In addition, 2 lane 16 gigabit per second may have a less area than the 1 lane 32 gigabit per second. Then we can fit more area to the cap to improve the power integrity in the SoC. Here are the summarized images of why we need a low speed in a SerDes. Even though we increase the data rate over time over several decades, from a few megabit per second to 224 gigabit per second line rate nowadays, we may need to revisit the SerDes speed and may need to reduce the speed for a few implications here. The first one is the required circuit performance compared to the device ability, including the undiagnosed passive elements, ILC. The second one will be a digital power from the CVF current related to the device performance described above. For example, the device strength might not be strong enough, and the gate fan-out could be too small to save the power. Therefore, the power could be quadruple instead of doubling in proportional to the double data rate. For the analog power, either the TX or RX driving loading and circuit complexity could be reduced a lot, owing to the low channel loss at the low data rate. One extra benefit of low power at a low data rate would mitigate the 16 nanometer to 3 nanometer fixed device self-heating and aging concern. Then eliminate the thermal runaway on the chip. We demonstrate the 2 lanes 16 gigabit per second may have 32 milliwatt less power than the 1 lane 32 gigabit per second. We finally also point out the area of 2 lanes 16 gigabit per second could be less than the area of 1 lane 32 gigabit per second if we can shrink the bump pitch without bump limit area. From all the PPA and design challenge images, we believe a low data rate could be the new trend in the future. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.